This is the third section of the methods in differential equations, and here we look at second order non-homogeneous differential equations. Now we know what a homogeneous differential equation is. Homogeneous is where you have your differential equation equal to 0. So homogeneous will be where you have your differential equation, let's call it dE, equal to 0. Non-homogeneous is where you have your differential equation equal to a function of x. Now the form of f of x could look like any of these here. So f of x could be just a constant, it could be linear, it could be a quadratic, it could be an exponential, or it could be one of these which is a combination of sine or cos. So basically the bit that's on this side, so I'll have a, let's write down what our differential equation might look like. So this bit we recognise like this. This bit will be f of x, so it's not 0 anymore, it's this f of x. So this part here could look like any one of these forms here. That's what f of x could look like. Okay, and this forms part of our differential equation which we need to solve. Now what we do is whatever the form of f of x, we then replace y with the form that goes with it over here. So once we've decided what form f of x takes, we then replace y with one of those forms there that's in the table. So if, I don't know, I had a differential equation, this was equal to 5, then I replace y, I'd say let y equal lambda. So e.g. if f of x equals 5, then I would say let y equal lambda. If f of x equaled let's say 2x squared minus 3, then I would say let, and I'd look at the table. So this is going to be a quadratic where actually q would be equal to 0. So I would then let y equal to lambda plus mu x plus nu, I think that is, nu x squared, not v. And let's just do one more so you can get the idea. If f of x was equal to negative 7 e to the power 4x, then I would let y equal to, so I look at the table here, so you do need to memorize this, it's not in the formula book. Y would equal lambda e to the kx, so lambda e to the kx. Now you can see I've got unknowns here, so these are all unknowns, I'm underlining here, and the way that we're going to find out those unknowns is actually now calculate dy dx from these things here. These are called the particular integrals. We'll talk all about this in a moment. So we'll calculate dy dx and d squared y over dx squared, then substitute into differential equation, to find the unknowns. Then our solution, the general solution, will be y equals to something called the complementary function, CF. Now the complementary function, this is basically when we find or we write down the auxiliary equation and solve. So the complementary function, this comes from forming and solving the auxiliary equation. So this is pretty much what we did in the last section. When you form and solve the auxiliary equation, that gives you the general solution to a homogeneous differential equation. That's what we did in the last section. And we call that the complementary function. So that's pretty much the same as what we did before. That's half of our answer, plus pi. Pi is short for the particular integral. And a particular integral is what we get when we solve this, when we find these unknowns. So when we have a non-homogeneous differential equation, our solution comes in two parts. The complementary function, which is basically where you imagine this is equal to 0 and you solve this using a previous method from section 7.2, and that gives us something called the complementary function, and we add to that the particular integral, which is what we get when we replace f of x, or from f of x we find the form of the particular integral, and then we go through this process and we work out the value of these unknowns in these particular integrals. Once we've done that, that will give us what's called the particular integral here, and we add the two together. So we're going to do plenty of examples so you can see what's going on. Okay, so in this example here, it says find a particular integral of the differential equations. So I'm not solving these fully. All I'm doing is finding the a particular integral. So that's the steps we were just talking about. So first of all, with the first one where I've got 3, so I look at my table for now until I've memorized it. So the form of f of x is like this, p, which means the form of the particular integral is lambda. So the first thing I do, I say let y equal lambda. Now from there I calculate dy dx, so I differentiate that, so that's going to be 0, and I differentiate that again, and that will give me 0. Now this I substitute into the differential equation. So if I do that, I will get 0 minus 5 times 0 plus 6 lambda equals 3, because it tells us that f of x is 3. Okay, so from here we can work out what lambda is. So what do I end up with? 6 lambda equals 3. So then lambda equals a half. Okay, so that's the form of the particular integral, is going to be a half. So that's my answer for part A. So part B, this time I have f of x equal to 2x. So I'll look at my table till I've memorized it. It's this form. So I will say let y equal lambda plus mu x. I differentiate that. So dy dx is going to be mu. Differentiate that again. And I get d squared y over dx squared equal to 0. I substitute this into this side of the differential equation. So it's going to be 0 minus 5 times mu and plus 6 times lambda plus mu x, and that equals 2x. Okay, so we're now going to solve this. A little bit more work than the previous one, but it should still be fairly easy to solve. So let's expand the brackets and see what we get. So I'll get minus 5 mu plus 6 lambda plus 6 mu x equals 2x. Now I can equate the coefficients, from here. So that means if I look at the x terms, 6 mu equals 2, which means that mu equals a third. Okay, so that's part of my answer there. Mu equals a third. Then I can substitute that in to the equation. So minus 5 times by mu, which is a third, plus 6 lambda, which we now need to work out, plus 6 times a third x equals 2x. Okay, simplifying that will give us 6 lambda equals 5 over 3, which will give us lambda equals 5 over 18. So we now can write the form of the particular integral, and so we go back to this. So it's going to be lambda plus mu x, or 5 over 18 plus a third x. So we'll just highlight that as our answer for that part. So now we'll move on to part C. So if we look at part C, we have 3x squared. So looking at the table, it's a quadratic, so the particular integral is going to be this form. So that's going to be lambda plus mu x plus nu x squared. So that's what I should write down. We're going to let y equals that. So let y equals lambda plus mu x plus nu x squared. So we then find dy dx. So that's going to be mu plus 2 nu x, and then we find d squared y over dx squared. So that just be 2 nu. It's made up more like a Greek letter like that. That gets substituted into the differential equation. So we will try and squeeze it in here. So that will be the second derivative, which is 2 nu minus 5 times the first derivative, which is lambda plus 2 nu x plus 6 times y. So it's going to be 6 lambda plus mu x plus nu x squared. And that's going to equal 3x squared. So I'll just put that here, equals 3x squared. So now we solve this. Now what we'll do is we'll expand the brackets, and then I'm going to collect terms of the same coefficients. I think that will probably be the quickest way. So we got 2 mu minus 5 mu minus 10 nu x plus 6 lambda plus 6 mu x plus 6 nu x squared equals 3x squared. Right, so if I collect like terms, let's look at the x squared terms and look at their coefficients. So let's do this different colour. So I would have 6 nu equals 3, so then I get nu equals a half. Let's just highlight that so I don't lose it. Now let's look at the x terms. Now on one side the coefficient is going to be 0, isn't it? Yeah, because there's no x terms on this side. Over this side the coefficient of the x terms are going to be minus 10 nu and 6 lambda. So these two, I want to make sure I don't miss anything out. Whoops, not that one. This one here. So that'll be negative 10 nu plus 6 lambda equals 0. So we now want to solve that. So that'll be 10 nu equals 6 lambda. Now we know that nu is a half, so that's basically 5 equals 6 mu. So mu equals 5 over 6. So again, we'll just highlight that so we don't lose it amongst all our working. And lastly, I will compare the number terms. So number terms, let's underline those. So that's going to be these two, this one, and that's going to equal 0. So I will have 2 nu minus 5 lambda plus 6 lambda. I don't know if I just said lambda there, I didn't mean to say it twice, equals 0. Now we have nu is a half, so 2 times a half is going to be 1, minus 5 lambda, so it's going to be 5 times 5 over 6, which is going to be minus 25 over 6, plus 6 lambda equals 0. So that means 6 lambda equals, just work this out on my calculator, that's 19 over 6, which will then give us lambda equals, we divide both sides by 6, 19 over 36. So our particular integral, when we replace lambda, mu and nu with the values that we've got, will be, so pi equals lambda, which is 19 over 36, plus mu x, so that's going to be 5 over 6x, plus nu x squared, so it's going to be half x squared. Okay, so that's our particular integral for part C here, like this. Now you might want to pause it because I'm going to clear the screen to give me space to do parts D and E. Okay, so part D, we have f of x now is equal to e to the power x. So we look at our table until we've memorized it. So the form of the particular integral, we make y equal to that. So we just do y equals lambda e to the kx. So we find dy dx. So that will be k lambda or lambda k e to the kx. And then we differentiate it again. And we'll have k squared lambda e to the kx. These get now substituted into the left hand side of the differential equation. So we will have the second derivative, which is k squared lambda e to the kx, minus 5 lots of the first derivative, which is k lambda e to the kx, then plus 6 lots of y, and that's just lambda e to the kx, and that will equal f of x, which is e to the x. Okay, so now on to part D, where I can see that f of x equals e to the x. So we need to have a look at our table here. Now notice in the example that we're doing here, the value of k here, k equals 1. So k is going to equal 1 over here. So we actually don't need a k in this case. We can say that y is going to equal lambda e to the x. Okay, so whatever power you have next to the x here goes on the other side. In this case, k is 1, so don't write lambda e to the kx, just write lambda e to the x. Yeah, whatever's are here, let's just clear that because it's very, very small. Whatever you have here needs to repeat it on this side. Okay, so repeat that power. Don't put the k in when it's not needed. K will be whatever that value is on the original question. Right, so from here I'm now going to work out dy dx. So that will be lambda e to the x. So very easy, that one. And when you differentiate it again, it's still going to be lambda e to the x. Yeah, it doesn't matter how many times you differentiate, you're going to get the same thing with this particular function. Right, so now substitute it into here. So the second derivative, which is this, minus 5 times the first derivative, which is basically the same thing, plus 6 times y, which is exactly the same thing, equals f of x, which is e to the x. So if we look at the coefficient of e to the x on both sides, on this side it's 1, so the coefficients on this side need to equal 1. So that plus that needs to equal 1. So I'll write that down, lambda minus 5 lambda plus 6 lambda has got to equal 1. The coefficients have got a balance on both sides. Now that will give us, I think it's 2 lambda. Lambda minus 5 is minus 4 plus 6, yes, so 2 lambda equals 1, which gives us lambda equals a half. So our particular integral, the form of a particular integral, is going to be a half e to the x. So we'll just highlight that before moving on to the last one, part E. Right, now on part E, where we've got f of x equals 13 sine 3x, I can see that it fits this last form here. Now don't be tempted to just write the particular integral as just this part, the mu sine omega x. You need the whole function. Yeah, so that's really important, otherwise everything's going to go wrong after that. So y equals lambda cos omega x plus mu sine omega x. So we'll now find dy dx. And in the example we're doing here, omega is 3, so let's put that in. Okay, so when we're doing these questions, actually it might be useful to write down what these different values are. So here we got omega equals 3. In the previous example that we did, k was equal to 1. So we can take those values over to the other side. Yeah, so here's what we set for y. Now we'll differentiate it, and we'll have 3 lambda cos, cos differentiated becomes minus sine, doesn't it? So it'll be minus 3 lambda sine 3x, and then plus 3 mu cos 3x. Now we differentiate again. So we've got to be careful with our sine and coses when we differentiate them. So differentiating this again, this will become minus 9 or negative 9 lambda cos to the 3x. And then cos differentiate becomes minus sine here. So I'll have minus 9 or negative 9 minus 9 mu sine 3x. These now go into the differential equation, so we're going to need a bit of space for this. So the second derivative, minus 9 lambda cos 3x minus 9 mu sine 3x. Then minus 5 lots of this. So minus 5 lots of dy dx, which is going to be this. And then we're going to add 6 lots of y, which is going to be this. And all of that is going to equal f of x, which is 13 sine 3x. So let's compare the coefficients. So let's start with the coefficients of the cos term. Now you can see on the right hand side the coefficient of cos is 0. On the left hand side the coefficient of the cos 3x terms are negative 9 lambda, and from the first term, then expanding the brackets. So let's just put some things here just to show you that I'm expanding brackets as I go along. Yep, so from the second bracket I'm going to get negative 5 times by this, so I'm going to get negative 15 mu. So negative 15 mu. Then from the last bracket I'm going to get 6 lambda. So plus 6 lambda equals 0. If I now compare the coefficient of the sine terms, so I can see, well, on the right hand side it's 13. On the left hand side it's going to be negative 9 mu. Then from expanding these brackets it's going to be plus 15 lambda. And then from the last bracket here it's going to be plus 6 mu, and equals 13. So now I want to solve these simultaneously. So I'll simplify them first before actually doing it on my calculator. So I will get from this one negative 3 lambda minus 15 mu equals 0. So that's one equation that I'm going to use. And from the second bit, I will get minus 3 mu plus 15 lambda equals 13. So as I said, I'm going to use my calculator to solve these. Right, so from that I get mu equal to negative 6, and lambda, just press the button, is 5 over 6. So you can use your calculator to help you solve these. So now I'm ready to write down what the form of the particular integral is. Now I've worked out mu and lambda, and they just get replaced into the form here. Yeah. So I will have 5/6 cos 3x. So 5 over 6 cos 3x. And then mu is negative of 6, so negative of 6 sine 3x. So negative of 6 sine 3x. So there we go. There's our particular integral for this one. So just highlight that. So now in this example, we're going to find the general solution. And a general solution, remember, is the complementary function plus the particular integral. Now, we found the values of the particular integrals for these different values of f of x in the previous example. So I'm not going to find all of those again. You can look back at the previous example, example 11, and then you can look at again, if you need to, how we work those out. But now, for now, I'm just going to write them down. So for part A, that was a half. For part B, that was 5 over 18. So I'm going to need a bit more space. 5 over 18 plus a third x. For C, the particular integral was, let's write it down here, 19 over 36 plus 5 over 6x plus a half x squared. For D, let's do that here, that was a half e to the x. And for the last one that we did here, this one was 5 over 6 cos 3x minus 1/6 sine 3x. Yeah, so you can always look back at how we did those. So all we need to do now is to form the auxiliary equation, so that's with a equal to 1, b equal to negative 5, c equal to 6. So the auxiliary equation is going to be m squared minus 5m plus 6 equals 0. Now I think we can solve that quite easily. Let's have a look. Two numbers that multiply to give me 6 and add to give me negative 5. So that's minus 3 and minus 2. So the solutions to my auxiliary equation are m equals 3 and m equals 2. So you might need to look back at the table to remind yourself how to do it, but then if you do, you'll remember that these are going to be the two roots, alpha and beta, 3 and 2, and the form of this equation when you've got two roots, basically when b squared minus 4ac is greater than 0, is y equals a e to the alpha x plus b e to the beta x. Yeah, so that's from the previous section. So that means that the general solution that I get, and this is what we call a complementary function, is going to be a e to the 3x plus b e to the 2x. Okay, so this thing that we've written down here is called the complementary function, and that was from the working that we did in the previous section. So all I need to do now for each answer is to add this complementary function to each particular integral. So all of my answers are going to start the same with this. So a is going to start like this, so is b, so is c, d and e. So to save some time, I'm just going to pause it and write down the complementary function for all of my answers. So there we go, like magic. So for each answer now, just put the particular integral at the end. So a, I just put plus half. B, I put plus 5 over 18 plus a third x. C, I add 19 over 36 plus 5 over 6x plus half x squared. D, I had half e to the x, and E, I add 5 over 6 cos 3x minus 1/6 sine 3x. So now this represents, these answers represent the full general solution to each one of these non-homogeneous second order differential equation with different values of f of x. So this first part we recognise from the previous section. We now add a little bit of extra working to get these particular integrals, and we add the two together to get the full solution for a differential equation of this type. Now this example and the next one illustrate a problem that could occur, and that's to do with terms that you get in your complementary function. If when you've worked out your complementary function you get a particular term in there, if that term occurs in the particular integral, you must multiply the particular integral by x or even x squared. Okay, so I'll write that down and you'll see that as we go through the example. Yeah, so I'll just write down here. So if after solving or finding, if after finding the complementary function, that's the CF part, you find that a term also occurs in the particular integral, that's the PI part, then you must multiply the particular integral by x, or maybe even x squared. So the complementary function and particular integrals are not of the same form. So let's work through this question and see what we get. So first of all, we're going to work out the complementary function. So we start with the auxiliary equation. Here A is 1, B is -5, C is 6. So the auxiliary equation is going to be m squared minus 5m plus 6 equals 0. So if I factorise this, I think I've done something like this before, it's -3 and -2. So m equals 3, m equals 2. So that means the form of my complementary function is going to be of the form y equals a e to the alpha x plus b e to the beta x, where alpha is 3 or 2 and beta is 3 or 2. Doesn't matter which way around. So I have my complementary function as y equals a e to the 3x plus b e to the 2x. I'll just highlight that. Now, when I get to the next bit to do the particular integral, if you maybe go back and have a look at the table, you'll know that if you get something of this form, e to the 2x, and maybe I might write it down just as a reminder. So when you get something like this, p e to the kx, yeah, if that's the form of f of x, the table says that we need to try something. The form of the particular integral is like this. So you might be tempted to, on this question, to say, right, okay, I have e to the 2x, so why not let's do lambda e to the 2x. But can you see that something like this already occurs in our answer? We've already got something e to the 2x, so we can't have the same terms occurring in the complementary function and the particular integral. So what I do is I go through this process here. I need to multiply this particular integral by x. So this time y isn't going to equal lambda e to the 2x, and y is going to equal lambda x e to the 2x. So you've got to watch out for that. Once you write down your particular integral, look to see whether that particular integral appears in the complementary function. In my case it does. So to stop having the same term in both, which we can't allow to happen because they could end up cancelling out, or you could end up putting them together, that would be wrong. We've got to multiply our particular integral by x, which is what I did. And I times that by x, well, not times that by x, but times this by x. Then I'll get this lambda x e to the 2x. So that's what I use, not just lambda x. Right, now we work out dy dx. And to do this, we're going to have to use the chain rule. Sorry, not the chain rule, product rule. So if I call this bit u and this bit v, then I will have u times by v dash, which would be 2e to the 2x, plus v times by u dash, which would just be lambda. So it might be worth just tidying that up a bit. So I'll have 2 lambda x e to the 2x plus lambda e to the 2x. Now we differentiate again to get d squared y over dx squared. So again, product rule. So if I call this bit u and this bit v, then I will have 2 lambda x times by v dash, which will be 2 e to the 2x plus v times by u dash, which will just be 2 lambda, plus that last term differentiated, which would be 2 lambda e to the 2x. So again, we will tidy that up, and we will have 4 lambda x e to the 2x plus 2 lambda e to the 2x plus another 2 lambda 2 to the 2x. Just notice these two terms here will end up being the same, so that will be 4 lambda. So let's just cross out the 2 and change that to 4 lambda e to the 2x. So there's a lot going on here, so I'll just highlight y here and dy dx, which is here, and d squared y over dx squared. So they're going to get substituted into the differential equation. So that's going to be 4 lambda x e to the 2x plus 4 lambda e to the 2x. Then I want to take away 5 lots of this, so I'll work that out straight away. So I'm going to multiply these by negative 5. So I'll get minus 10 lambda x e to the 2x minus 5 lambda e to the 2x, and then multiply all of this by 6. So I will just have plus 6 lambda x e to the 2x. That will equal f of x this side here, so e to the 2x. Right, okay, let's see if we can solve that then. So let's have a look. We've only got one unknown here, lambda. So we can solve by comparing the coefficients of the e to the 2x terms. So there's 4 lambda there, 5 lambda there. So that means that 4 minus 5, or 4 lambda, minus 5 lambda has got to equal 1, because that's the coefficient on the other side. So negative lambda equals 1, lambda equals negative 1. So we've got to highlight that, because we'll need that in a minute. Well, actually we'll need it now, because now we can put that into here for our particular integral. So that'll be negative x e to the 2x. So negative x e to the 2x. So actually, I won't highlight this. I'll highlight this here, because that is my particular integral. So the general solution for this is going to be, let's highlight in different colour, this part here, which is the complementary function, added to this part here, which is the particular integral. So all I need to do now is to write them next to each other. So the general solution will be y equals a e to the 3x plus b e to the 2x minus x e to the 2x. And I'm guessing you might be able to factorize that if you wanted to. Probably put e to the 2x outside the brackets, but it's not necessary. So this would be our solution, general solution for that differential equation. Okay, so we want to find the general solution to this. So first step is going to be finding the complementary function, which means the auxiliary equation with a equal to 1, b equal to -2, and in this case c equals 0. So the auxiliary equation will be m squared minus 2m equals 0. So that can easily be solved. We will get m, well, once we factorize it like this, I suppose. So yeah, m equals 0, m equals 2. When we have two real solutions, the form of our auxiliary equation is going to be like this. So remember, try and memorize these with alpha equal to 0, beta equal to 2. Now when we put alpha equal to 0 here, we'll get e to the power 0. So all of this just becomes 1, so we can just write it as a. We don't need to write e to the power 0. So y equals a plus b e to the power 2x. So this is our complementary function. Now we do the particular integral. We're only, well, we're sort of halfway through. So particular integral. Now when we see f of x equal to 3, when it's that form, we know that we try a particular integral of the form lambda. But just like the previous one, this is going to be a constant. We already have a constant term in our complementary function. So you remember what we do? We multiply this by x. So we haven't got any constant times x terms in our complementary function, so we just multiply that by x. So we try lambda x. So this is what we're going to make y equal to. Yeah. So multiply by x. So we don't have the same type of term in the particular integral. Now, if for some reason there was already a constant times x term in the complementary function, so I don't know, let's say this had 3x in it, or cx or something like that, then you would multiply lambda by x squared, yeah, to get a different type of term. Right, so we've got y equals lambda x, rather than just y equals lambda. dy dx will be lambda d squared y over dx squared is going to be 0. Substitute those into the differential equation. So I'll have 0 minus 2 times dy dx, which is lambda. There's no y term in here, so we don't need to put y in. So that's just going to equal 3. Okay, which means lambda is going to be -3 over 2. So we've got our value of lambda. So that gives our particular integral, going back to this, we've now worked out lambda as -3 over 2x. So I'll just highlight that. That's our particular integral. So the last step now is our answer is the complementary function plus the particular integral giving us the general solution as y equals a plus b e to the 2x minus 3 over 2x complementary function plus particular integral. Okay, you should now be able to do exercise 7c on pages 161 to 162. So what's here is the table that we can use to help us find the particular integral. Remember what we need to do, we need to watch out for terms already in the complementary function, and if you've got terms that are already in the complementary function, then you need to take your particular integral and times it by x, and if that term's already in the complementary function, you take that term and multiply it by x squared. Okay, it's more likely it's just going to be you multiply by x, so watch out for something like that. And just to recap how we solve our differential equations, so we form and solve the auxiliary equation to find the complementary function, and then once we've got the complementary function, our general solution is going to be our complementary function plus the particular integral, and of course that will be y equals that.